basics of trigonometry. Trigonometry. It sounds like a very complicated topic, but you're going to see that it's really just the study of the ratios of sides of triangles. The trig part of trigonometry literally means triangle, and the metry part literally means measure. So let me just give you some examples here, and I think it'll make everything pretty clear. So let me draw some right triangles. Let me just draw one right triangle. So this is a right triangle. When I say it's a right triangle, it's because one of the angles here is 90 degrees. This right here is a right. That right there is a right angle. It is equal to 90. It is equal to 90 degrees. And we'll talk about other ways to show the magnitude of angles in future videos. So we have a 90-degree angle. It's a right triangle. Let me put some lengths to the sides here. So this side over here is maybe 3. This height right over there is 3. Maybe the base of the triangle right over here is 4. And then the hypotenuse of the triangle. The hypotenuse of the triangle over here is 5. You only have a hypotenuse when you have a right triangle. It is the side opposite the right angle, and it is the longest side of a right triangle. So that right there is the hypotenuse. Hypotenuse. You probably learned that already from geometry. And you can verify that this right triangle, the sides work out. We know from the Pythagorean theorem that 3 squared plus 4 squared plus 4 squared has got to be equal to the length of the longest side. The length of the hypotenuse squared is equal to 5 squared. So you can verify that this works out. This satisfies the Pythagorean theorem. Now with that out of the way, let's learn a little bit of trigonometry. So the core functions of trigonometry, we're going to learn a little bit more about what these functions mean. There's the sine function. There is the cosine function, and there is the tangent function. And you write sine, cos, or sin, cos, and tan for short. And these really just specify for any angle in this triangle, it'll specify the ratios of certain sides. So let me just write something out. This is a little bit of a mnemonic here, so something just to help you remember the definitions of these functions. But I'm going to write down something. It's called SOHCAHTOA. SOHCAHTOA. And you'll be amazed how far this mnemonic will take you in trigonometry. So we have SOHCAHTOA. And what this tells us is, so tells us that sine is equal to opposite over hypotenuse. Opposite over hypotenuse. Opposite over hypotenuse. It's telling us, and this won't make a lot of sense just yet. I'll do it a little bit more detail in a second. And then cosine is equal to adjacent over hypotenuse. Cosine is equal to adjacent over hypotenuse. And then you finally have tangent. You have tangent. Tangent is equal to opposite over adjacent. Opposite over adjacent. So you're probably saying, hey Sal, what is this, all this opposite, hypotenuse, adjacent? What are we talking about? Well, let's take an angle here. Let's take an angle here. Let's say that this angle right over here, this angle right over here is theta, between the side of length 4 and the side of length 5. This angle right here is theta. So let's figure out what the sine of theta, the cosine of theta, and what the tangent of theta are. So if we want to first focus on the sine of theta, we just have to remember SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. So sine of theta is equal to the opposite. So what's the opposite side to the angle? So this is our angle right here. The opposite side, if you just go the opposite side, so not one of the sides that are kind of adjacent to the angle, the opposite side is the 3. If you're just it's opening onto that 3. So the opposite side is 3. And then what's the hypotenuse? The hypotenuse, well, we already know the hypotenuse here is 5. So it's 3 over 5. The sine of theta is 3/5. So someone says, hey, what's the sine of that? It's 3/5. And I'm going to show you in a second that the sine of theta, if this angle is a certain angle, it's always going to be 3/5. The ratio of the opposite to the hypotenuse is always going to be the same even if the actual triangle were a larger triangle and a smaller one. So I'll show you that in a second. But let's go through all of the trig functions. Let's think about what the cosine. Let's think about what the cosine of theta is. Cosine is adjacent over hypotenuse. So remember, this. Let me label it. We already figured out adjacent, which is 4 over the hypotenuse. 4 over 5. Now let's do the tangent. Let's do the tangent. The tangent of theta. Opposite over adjacent. The opposite side is 3. The opposite side is 3. What is the adjacent side? We already figured that out. The adjacent side is
Okay, back. Yep. And nobody's on news.
is 4. So knowing the sides of this right triangle, we were able to figure out the major trig ratios in a random Greek letter. So let's say it's xi. I know it's a little bit bizarre. Once again, the lengths of this triangle are, we have length 4 there, we have length 3 there, we have length 5 there. The last example, we used this theta. So let's do another angle. Let's do another angle up here. Let's do another angle up here. Let's call this angle, I don't know, I'll think of something, a random Greek letter. So let's say it's xi. I know it's a little bit bizarre. Theta is what you normally use, but since I already used theta, let's use xi. Actually, even
Okay.
call this hypotenuse. You have the tangent is opposite over adjacent. SOHCAHTOA. Tangent. SOHCAHTOA definition. Let's just do a ton of more examples just so that we make sure that we're getting this trig. 9 plus 16. 49 plus 16. See, 49 plus 10 is 59. Plus 6 7. And let's say the length of this side up here, let's say that that is 4. And let's figure out what the hypotenuse over here is going to be. So we know, let's call the hypotenuse h. We know that h squared is going to be equal to 7 to the square of 16. 49 plus 16. See, 49 plus 10 is 59. Plus 6 is 65. It is 65. So this h squared, we write h plus 10 is 59, plus another 6 is 65. Or we could say that h is equal to, if we take the square root of both sides, square root of 65. And we really can't simplify this at all. This is 13. The trig function. Always want to write down, at least for me it works out to write down, SOHCAHTOA. So, you know, about some type of Indian princess named SOHCAHTOA or whatever, but it's a very useful mnemonic, so we can apply SOHCAHTOA. Let's say we wanted to find the cosine. We want to find the cosine. Of our cosine equal to, well, we know that the hypotenuse is this side over here.
Oh, yes.
So it can't be that side. The only other side that's kind of adjacent.
SOHCAHTOA. Anyways. Oh.
To it that isn't the hypotenuse is this 4. So the adjacent side over here, that side it's literally right next to the angle. It's one of the sides that kind of forms the angle. It's 4 over the hypotenuse. The hypotenuse we already know is square root of 65. So it's 4 over the square root of 65. And sometimes people will want you to rationalize the denominator, which means they don't like to have an irrational. Rational number in the denominator, like the square root of 65, denominator by square root of 65. This clearly will not change the number because we're multiplying it by something over itself, so we're multiplying the number by 1. That won't change the number. This clearly will not change the number because we're multiplying it by something over itself, so we're multiplying the number by 1. That won't change the number, but at least it gets rid of the irrational number in the denominator. So the numerator becomes 4 times the square root of 65. And the denominator, square root of 65 times square root of 65, is just going to be 65. We didn't get rid of the irrational number. It's still there, but it's now in the numerator. Now let's do the other trig functions, or at least the other core trig functions. We'll learn in the future that there's actually a ton of them, but they're all derived from these. So let's think about what the sine of theta is. Once again, go to SOHCAHTOA. The SO tells us what to do with sine. Sine is opposite over
opposite over hypotenuse. 7 over squares. 65, right? So then multiplying it by 2.
hypotenuse. Sine is equal to opposite over hypotenuse. Sine is opposite over hypotenuse.
Yep.
So for this angle, what side is opposite? You just go opposite it, what it opens it to. It's opposite the 7. So the opposite side is the 7. This is right here. That is the opposite side. And then the hypotenuse. It's opposite over hypotenuse. The hypotenuse is the square root of 65. Square root of 65. And once again, if we wanted to rationalize this, we can multiply it times the square root of 65 over the square root of 65. The numerator will get 7 square roots of 65, and in the denominator, we will get just 65 again. Now let's do tangent. Let us do tangent. So if I asked you the tangent of theta, once again, go back to SOHCAHTOA. The TOA part tells us what to do with tangent. It tells us that tangent is equal to opposite over adjacent, is equal to opposite over adjacent. So for this angle, the trig ratios for theta. Let's do another one. I'll make it a little bit concrete, because right now we've been saying, oh, what's tangent of x, what's tangent of theta? Let's make it a little bit more concrete. Let's say, let me draw another right triangle. There's another right triangle here. Everything we're dealing with, these are going to be right triangles. Let's say the hypotenuse has length 4. Let's say that this side over here has length 2. And let's say that this length over here is going to be 2 times the square root of 3. We can verify that this works. If you have this side squared, so let me write it down, 2 times the square root of 3 squared plus 2 squared is equal to what? This is 2, this is going to be 4 times 3 plus 4, and this is going to be equal to 12 plus 2, this is going to be 4 times 3 plus 4, and this is going to be, this is 2, this is going to be 4 times 3 plus 4, and this is going to be equal to 12 plus 4 is equal to 16, and 16 is indeed 4 squared, so this does equal 4 squared. It does equal 4 squared. It satisfies the Pythagorean theorem. And if you remember some of your work from 30, 60, 90 triangles that you might have learned in geometry, you might recognize that this is a 30, 60, 90 triangle. This right here is our right angle. I should have drawn it from the get-go to show that this is a right triangle. This angle right over here is our 30-degree angle. And then this angle up here is a 60-degree angle. And it's a 30, 60, 90 because the side opposite the 30 degrees is half the hypotenuse, and then the side opposite the 60 degrees is a square root of 3 times the other side that's not the hypotenuse. So with that said, we're not going to, this isn't supposed to be a review of 30, 60, 90 triangles, although I just did it. Let's actually find the trig ratios for the different angles. So if I were to ask you, or if anyone were to ask you, what is the sine of 30 degrees? And remember,